चलो शुरू। ठीक है। Okay. So last time we ended with this. So under this Mobius transforms group, if you take any circles in C infinity, they will end up going to circles in C infinity. So next is we'll look at the we'll look at transitive properties of this. So what is the meaning of transitivity? Suppose you have a set of maps. You have a set of maps from X to X. So like given a set of maps from X to X, I will call this transitive if you take any 2 points in your set, there will exist a map taking X to Y. Okay. Okay. So proposition now is the Mobius group. It is uniquely triply transitive. What does this mean? This means so if you give me any 3 distinct points in C infinity and another triple of 3 points, like so this is your first triple. This is the second triple. So if you give me any 2 triples like this, I can find a map, unique map, which takes Z1 to W1, Z2 to W2, and Z3 to W3. Okay. So how does the proof? So what I will do in the proof is, so So what I will prove is I'll take the 3 points 0, 1, and infinity, and I will show that these can be taken to any three distinct points Z1, Z2, and Z3. So once you prove this, you can prove that you can take any 3 points to any 3 points by taking first take 0, 1, infinity to these three, then again find another map taking 0, 1, infinity to the other three maps, then just invert one of them and compose. Okay. So how? So what? So if you consider this map, if you consider this map, you will see that M of Z1 is 0, M of Z2 is 1, just 1 minute. Okay. So M of Z3 will be infinity. Again, as Chinmay said, if one of the Zi's is infinity, you'll have to take it case by case, and some of the factors here will not appear, but the map will still be a Mobius map. Okay. So if you have this map, M inverse works here. So for uniqueness, for uniqueness, so it will be enough for us to prove that any map of the form M of Z equal to so any such map doing this will be the identity. You can do this by just substituting, and you can just look at m of 0 equal to 0, m of 1 equal to 1. Like if you substitute the equation az plus b here, you'll get conditions on A, B, C, D, which will turn out to which will make sure that M is the identity. Okay. So we have now proved that the Mobius group is triply transitive, uniquely triply transitive on C infinity. Okay. Okay. So next is so next one is the Mobius transforms take circles in C infinity to circles. So this group acts on the set of circles. And the claim here is you give me any circle, I can find a Mobius transform taking it to any other circle you want. Okay. So how do we do this? Okay. So you will be given two circles and you want to get a map taking one to the other. So from the first circle, pick three distinct points and pick three distinct points from the second circle as well. So now you can find a unique Mobius map taking these 3 points to the next 3 points. Okay. So the claim is that this will work. This map will work because okay. Okay. So we have the first 3 points going to the second 3 points. We know that Mobius transforms preserves circles, and given 3 points in C infinity, it always determines a unique circle. So the circle through the first 3 points will be taken to a circle, but it will also go through the second 3 points, which means the first circle is taken to the second circle. Okay. It is also important that there is so Okay, this is also important. So now we can take any circle to any other circle. So finally, we will need this one. Uh, so this Mobius transforms, they are also transitive on disks. What are disks? So if you take a circle in C infinity, by Jordan Brouwer, it will separate the sphere into two halves. Both halves will be disks. So what I'm saying now is, given any disk, I can take it to any other disk. So uh, uh, the steps to do this is, given any disk, you will have its boundary, which will be a circle, right? So first step will always be to take the boundary circle to the boundary circle, which we can do. Now the point is, we have to make sure the interior also maps to the correct interior, right? Because these Mobius transforms, they are homeomorphisms of the sphere. Now once you take one circle to the other circle, the two disks in the first sphere will go to the two disks bijectively, but you don't know which disk it will go to. So we just have to make sure we flip it in the right manner. So true. So without loss of generality, we can assume that the boundary of this given disks is the circle, the unit circle S1 in C infinity. This is because you can compose and like pre-compose and post-compose by one of the maps you get here, like one of these maps. Okay. Then, okay. So now the point is, now there are two issues, right? So C infinity to C infinity, uh, you know. So let me assume this is S1 in C infinity. Now when I cut this, when I remove the S1, my disk would have been either this one or the bottom one, right? Uh, okay. So let me assume my given disk is this given disk. So now the second disk, there are only two options for the second disk. It is either this one or it is this one, right? So if we wanted to take D1 to D2, we will just take the identity map. If we wanted to take D1 to D3, we will take the identity. Oh no, we will not take the identity. We'll just take the map 1 over Z. Okay, you can verify that this will flip. Okay. So more precisely, so
Karthik, will minus z work? Minus
minus, yeah,
or
minus also, no,
no?
no, minus z will preserve, like it will take d1 to d2. Yeah, like it for d1 to d2 minus z you can take.
What is d2? D2 is the
So wait, so if you take c infinity minus this s1, you can think of it as there are two components, right? One is the bounded component, the other one is the unbounded
okay.
component.
The above one is d2. Okay, fine.
Yeah,
Uh,
yeah. So like if you are trying to take the bounded component to the bounded component, minus z is also fine.
Okay. Yeah. Yeah. Yeah.
Okay. So it is basically d1 going to d1 itself, or it is going to the other disk, which is flipping by 1 over. Okay. So now we have also proved that any disk in C infinity can be taken to any other disk. Okay. So in particular, uh, you can find a Mobius map taking the upper half space to the unit ball. Okay. I had to clarify something from last time. Badri asked a question about equivalence classes, so let me make that clarification. So as I said last time, that you take any matrix in GL2C, that will give you a Mobius transform just by taking the entries AZ plus B by CZ plus D. But this correspondence between matrices and Mobius transforms, it is not one-to-one. For example, if you take the identity matrix and the minus identity matrix, you will see that both these give the identity Mobius transform. Like as functions, the Mobius transformation you get, they are the same, but the matrices giving them, they are different. So So we are just interested in Mobius transforms as a function. So we don't really care about the different representations of the matrices. So you can think of it as we are looking at GL2 mod some equivalence relations. Like these two, like, like these two will be equivalent, and like you can give a proper equivalence relation, but I will not give it right now. It's not that important. Anyway. Uh, So now we proved that we can take any disk any disk in C infinity to any disk. So in particular, um, so since the upper half space is also a disk, we can there will be a lot of there will be Mobius transforms taking the upper half space to upper half space itself. Now we are interested in looking at all the Mobius transforms taking H to it. Uh, so okay, so now we will restrict ourselves to Az plus B by Cz plus D, where all the coefficients. Okay, so uh, let's say first question is where does this map take the real line? So the real line. So if Z is real in your so if Z is real in this formula, you will end up getting a real number. Right? You'll also have to be careful because infinity might come up. So what I will say is R union infinity will be taken to R union infinity by this map. So okay, so R union infinity is a circle. So this thing preserves this circle, and so since it preserves this circle, now it will either flip the upper half space to the lower half plane, or it will preserve it. So that is where this second condition comes in. So because of the second condition, you will get that H will always go to. Okay. Let me just say this is X. So what would we end up getting? So we ended up proving that any map from any Mobius transform coming from GL to R plus, like 2x2 real matrices with positive determinant, will take our H closure to H closure. Okay. So we notice that if you give a matrix and you multiply it by alpha, our function does not change. So we can choose alpha in such a way that the determinant becomes 1. Okay, so like you can take alpha to be square root of 1 by square root of determinant. So by doing this, we can reduce the matrices we need to consider to SL2R. Okay. But our minus identity matrix is still in SL2R, which also gives the same, it also gives the identity Mobius transformation. So since minus I gives us again the same Mobius transformation, I can kind of quotient our matrices out by that. And so this matrix group will be called, this will be called PSL2R. And once we have this, so this correspondence between PSL2R so this correspondence is 1:1. Like you take any matrix in PSL, any element of PSL2R, it will give a unique Mobius transformation preserving head. Okay, this I am skipping.
Yeah, so PSL2R, this is the group of automorphisms on H if we take H as a Riemann surface, right?
Yeah, that yeah.
Yeah, so
later. Yeah.
What is the significance of this thing in I mean, what is the notion of automorphisms in hyperbolic geometry?
So the notion will be isometries.
Ah, okay, okay. So it
Yes.
would be the same thing or something different.
So this Mobius groups will be isometries.
Okay.
So that has like a matrix, let's say representation or something. Okay. But we don't know this yet. We don't know this. Okay.
So is this map also bijective, like surjective?
Yeah, this is bijective. Yeah.
Okay, but we didn't prove that.
And it's if you take any Mobius map, it will have AZ plus B by CZ plus D. So you take the entries of that, you will get a matrix.
Okay, 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 okay.
Yeah.
Yeah.
So one last proposition for this is okay. What I'm saying now is the Mobius transforms preserving H. They act triply transitive on the boundary. So we had earlier proved that the Mobius transformations, all of them, like the ones coming from GL to C, they are actually triply transitive on the whole C infinity, or on the whole of C infinity. But now since we have restricted ourselves to a smaller group here, our transitivity property is also restricted, but we still have triple transitivity on the boundary of the I will just give you the map, you can verify it. Okay. So given A1, A2, A3, okay, this is important. So given A1, A2, A3 in clockwise direction, I can take this map. This will take A1, A2, A3 to 0, infinity, and 1. And this will also belong to. Okay.
What do you mean by clockwise direction?
So if you have the upper half space like this, and if you have 3 points, like clockwise direction, I want A1, A2, A3.
Okay.
If one of your points happen to be infinity, if it happened to be infinity, say, then the order is again this way.
Okay.
A1, A2, and A3. Okay.
Yeah. So is it necessary to get the determinant positive or what?
Yeah, this is for orientation preserving and getting positive determinant.
Okay.
Yeah. Okay. Now, so far we have not used the hyperbolic metric anywhere. This was just talking about Mobius transforms and circles. Now we will start looking at lengths and distances. So recall we had a Riemannian metric on the upper half space called the hyperbolic metric. Now I will start defining lengths here. So let so if you have any smooth curve in the space, I will define the length of this curve to be, so first you take gamma prime at each point. So gamma prime will be an element of the tangent space. So on the tangent space, you have a norm, which is not the usual norm. It is this hyperbolic norm. I mean, hyperbolic inner product, which gives a norm. So you take the length with respect to that norm, then you integrate this. Okay. So if I um, so if I write, if the coordinates of gamma was okay, length um, so this is how you will get the, oh sorry, I missed. Yeah. So if you like plug like xt and yt into this formula here, you will get this. But if it is not clear how to deal with Riemannian metrics, just take this to be the definition of length for now. Okay.
Is there a mod yt in denominator? Like you're taking square root, so.
No, yt is always positive because it's in upper half space.
Oh yes, okay.
Yeah. Okay. So this is length of two curves, length of a curve. So okay. Now, so I will define the hyperbolic distance now. So So given any 2 points in the upper half space, I will define the distance to be, you take any curve, like you take all the curves connecting Z and W, all the smooth curves, then take the length of those and take infimum over that. Okay, so the distance between Z and W is like the length of the shortest curve. Right? This infimum might not be realized, but it will always exist. Okay. So only thing you have to verify is, okay, you have to verify symmetry, non-negativity, and triangle inequality. I will just leave this as exercise. So I will define, so given any curve between W and Z, I will say it is a geodesic if the length of the curve is equal to the distance between them. So basically, I'm saying if a gamma is called geodesic if it is the length minimizing curve. One thing to note here is, so this is not actually the real definition of geodesics that people use, but in our case, this turns out to be something equivalent. Okay. Okay. I think I'll stop here today. Are there any questions?
Yeah, regarding the same thing. So you said that isometric maps, I mean they are the set PSL2R, right?
Yeah.
So are there any relation between the isometric maps here and the holomorphic maps in the, as if you take it as a Riemann surface? I mean in the usual sense in C2, if we forget about the Riemann surface thing. So isometric maps here, are they holomorphic in the usual sense?
Yeah, see, because since it is like AZ plus B by CZ plus D, it is rational function, right? So rational
Yeah,
function holomorphic.
yeah, these things are holomorphic. No, I am thinking in general. Are all isometries are the Mobius transformation? I mean, all the isometries,
Of
not
hyperbolic
the whole
space.
C infinity, not H.
So C infinity, there I have not defined any metric there.
Okay, 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 okay. You haven't.
Our metric is only on upper half space. But like if you just give it the Euclidean metric on the sphere,
Huh, huh.
uh, then the isometries are also holomorphic. They are like biholomorphic.
Okay.
Yeah. Yeah, but in our case, we are just restricting to the upper half space, and the maps are just uh, like the rational functions, right? Those are holomorphic. They actually turn out to be biholomorphic also.
Okay.
Yeah.
And does the conformal mapping thing occurs in this hyperbolic geometry? I mean, angle preserving thing.
Oh yeah, so yeah, I should maybe have said this. If so, the special way we have defined our Riemann metric, it is an inner product, right? And our
Yeah,
isometries
yeah.
will be preserving those inner products. And so
Okay.
our angles we measure using the inner product. So
Hmm.
the angle will also be preserved.
So if you get a conformal map in C infinity, I think it is holomorphic.
Conform. Conformal map in scene. Yeah, I think.
Locally invertible conformal, something like that.
Yeah, I think all the conformal maps between C infinity to C infinity, they are all Mobius transforms.
Okay.
But that is slightly harder to prove. Any other questions?
So how do we go about showing this is a metric?
So symmetry is symmetry.
Yeah, symmetry is fine.
Positivity.
No, for instance, showing like distance between any two distinct points is non-zero, those kinds of things.
Distance between
Two distinct points is non-zero.
two distinct points is non-zero. How would you do that?
I think the distance, like the Euclidean distance, is always like the length of the. So there will be semicircle, like a curve. Okay, that's a curve. Hmm.
No, I think so. You can bound this length of this curve below by the Euclidean thing, and you can
Yeah,
curve it.
yeah. I
Oh,
think.
okay.
Yeah. Like so if you restrict your space to just like y is greater than some constant k,
Hmm.
then you can bound your hyperbolic metric on both sides by the Euclidean metric.
Yeah, we can just take the small minimum of the imaginary part of both points.
Yeah. See, because y is in the denominator, right? If you bound it below, then you will get like a bound.
Still.
It makes sense. See, Euclidean length is what? It's just the everything without the denominator. Like this integral without the denominator. Is that clear?
Yeah, okay.
Okay. Yeah.
And the triangle inequality, like what will we be do? What will we do? I mean,
Triangle
so
inequality would have been easy if I said piecewise smooth curves. Like you will take one curve like this, but you can also approximate like piecewise smooth curves by smooth curves.
okay.
I mean, I can at any point I can just replace smooth by piecewise smooth, and everything will still be the same.
Okay.
Okay.
So geodesic should be smooth, or it can be piecewise smooth.
Geodesics. So this is not the correct definition, but when they define it correctly, it will be smooth.
Okay.
Yeah. And yeah, I don't know if there can be piecewise smooth geodesic. I'm not sure though. I'm not sure. There might be some metrics where you can have piecewise smooth geodesic.
Okay.
Yeah. Okay. So we will meet again on Thursday.